So, good morning everybody. My name is Jean-Louis Baji, and our group is Group 9 for the ECE machine for the senior design. And my group members are Aisha El Shafi, Corey Mattis, and then Zui. This is Aisha. So, we're going to go ahead and start our slide. So, the purpose of our design was to put together an ECG machine that would be doing the following. And process and compute 5 input signals from a human being, generate at least one clear ECG output signal, send this output signal to be processed, then be stored in a database, and then retrieve that database wirelessly and have it displayed on an Android cell phone. And then finally, our system is supposed to be able to be powered with or without AC. So our group have undertaken a pretty complex and time-consuming project this semester. Numerous times we have had actually to review our project and kind of like make some adjustment. But overall, actually, from 90 to 95%, we guessed actually our design actually came out pretty well. In the next few slides, I will be the one actually starting to go over the part that I've actually configured, which is the ECG input signals and then up to the output signals that actually will be sent to be processed to be by the Android and then displayed on the Android cell phone. And then Aisha is going to come to talk about the power that the power supply that she actually built to be able to power the whole system. And then Corey would actually talk about the software program that actually he put together to be able to run the whole thing. And then Zui at the end will come to buckle up the system, our presentation by talking about the application that he has built together for our ECG machine. So as you can see, over here we have a prototype of 5 electrodes input signal. This is actually how we put it together, and in our case we follow the convention like white, black, red, and brown, and green that will be put together for a person to generate the signals. So, and they all go depending on where they're called, like right arm, left arm, right leg, left leg, and then the V1 lead. So this is actually the schematic of the ADA's 1298. This is the input. We have actually a 15, the DB15 input connector where our signal will be coming in. And this is actually an example of some of the protection that we have using the diodes. And this is just another closer look of the protection diode, just to avoid the current actually coming back into the person if it's connected to an AC. And over here, it shows this is our ADH 1298 chip. So the connection from the input signals all the way to the ADH 1298. And this is a register assignment. So we use this actually to configure our own register, our own ADH 1298. So in our particular case, this is the configuration that actually we followed, showing the address for each particular register and then the hex configuration that actually was able to configure. And this configuration gave us one of the best actually signal we came up with. And here, this is the output protocol for the ADH 1298, how it functioned when it got done ready, the chip select, and then the clock. And in our case, we actually disable all the channels. We have 8 channels possibility for the ADH 1298, but in our case, we use the channel 2 and channel 3 to be able to display our output. And to finish my part, this is a little video of myself actually demonstrating how we connect each other and up to the point where we get actually the signals that actually comes out. So hopefully enjoy the video while Corey is going to take over. Actually, Aisha. Yes. Aisha. So as you can see, this is basically the signal that we pulled out from just that simple connection.
Hi. My part is to design a power supply to feed the systems. The main purpose of the power supply is to feed 3 different outputs with different voltage and current. One is 9 volt to power the mega board. The 6 volt is to power the part that John Louis talked about. And the last one is 5 volt to power the Yule Arduino. This is a breakdown of the circuits, value of the resistor, the way we configure it, and the way we measure the output from the circuit. The protection we did for the circuit, we have like 3 fuses. One, before the fuse we have a switch. We have fuse 1 to protect the input for the transformer. Fuse 2 is to protect the output from the transformer, and the third, last one, fuse 3, is to protect the DC from the rectifier to the other regulators. Here, this is actual pictures. The system is meant to power from AC. If the AC fails, the backup battery should get in immediately. So the green one, the green LED is AC, and then when we turn the switch off, actually there is switch for this circuit, it's over the battery, and we couldn't find a exactly 9 voltage rechargeable battery, so we use batteries in series, and the yellow one is when the AC failed or turn off, the battery will automatically feed the system. The same pictures from previous slides, we show it here in the diagrams. We show the rectifier with the diodes, and we show the way we connect the LED and the way we calculate the resistor to the resistor LED. One for the battery and one for the AC system. So, for this power supply, we had many problems. We have heating, especially for the voltage regulators. We have discontinuity. But the first time we didn't know why that happened. Fuse just blown away. Then one of the solutions to get the 9 volts not to overheat, we figured out that the 9 volt need to be powered with a power. The input should be less than the output by 3. So that means we need 12 volts at the end of resistor 3, and then we use the voltage regulator. The resistor 3 is the first resistor, and the combination of all the resistor is the second to figure out the voltage regulator to find the output. Go. For the second, no, go back, sorry. For the 6 voltage regulator, this is 9. For the 6 voltage regulator, actually, we try to solve it the same way. We try to find the voltage regulator, get the 3 output voltages different. The difference of 3 between the input and out is still heated. So we replace the linear voltage regulator, the LM7806, by another voltage regulator, LM3170, that has internal protection, internal current protection, thermal protection, heating, and the way we calculate the resistor is shown in the calculation down, and that work. Last, the 5 voltage regulator, the voltage divider worked for the 5 voltage regulators, but the problem was still we didn't get the exact amount of the current we dream of. We're still a little bit off by like 1 to 1.5%. So, go. For the way we measure the output current and voltage, we measure across the resistor to find out the voltage. We play with the variable resistor, and we have a table that showing the different amount of resistors according to this voltage, but the current would be calculated. The problem was all the resistor was when the resistor has like less than 3 watt power, the resistor or the fuse blown up. So we use this, although it's not convenient, but this is work. Sometimes we would use like 2 resistors in parallel to get the current separated, and this is what we did for. Now
My part is the data collection portion of the project. At the top you can see we have an Arduino Mega, an Arduino Yun is to the left there, and external SD cards to the right. There's also a couple LEDs for user interactions and an AND gate. In the first stage, the setup stage, both the Mega and the Arduino Yun set up their different components. The Mega sets up the ADS by sending it different configuration bits, as shown earlier by John Louie. The Yun, in the meanwhile, sets up its connection between the Arduino side and the Linux side on the microcontroller. All this is happening while yellow light is showing to show the user that this is the setup stage. And once each of the microcontrollers is ready, it will send a 1 out to the AND gate. When a 1 is received back from the AND gate, both Arduinos are synced up and ready to continue with the program. In the next stage, the collection stage, a green light will show to the user to tell the user that we are now collecting data. During this period, the Mega will collect data and store each character into a text file, which is then stored on the external SD card. And at the same time, the Yun will create a times.txt file and take 1-minute intervals from the actual time and put it into this file as a string. Go back, please. Back the other way. This will then be used to create 31-minute files later to be uploaded to Google. Next is the transfer stage. The transfer stage has a violet light to tell the user that they are able to unplug themselves from the ECG, but that they shouldn't turn the ECG off. During this stage, the 30 text files I explained before will be created and stored on the Yun's SD card, each one of them holding 60,000 points of data, which is equal to 1 minute. In this stage, the Mega then transfers all the data from its SD card to the Yun's SD card, and this is done through a software serial port because the Arduino Yun does not have the capability to do more than one real serial connection. The final stage is the upload stage, and in this stage, blue light is given to the user to tell the user this is nearing the final stage of the program. The Mega falls into a wait state, which means it just waits for the user to be done with the whole rest of the thing, while the Yun uploads each of the 31-minute files to Google. Due to the Yun's low memory, this is actually done with a Python script, which is held on the Yun's SD card. And then, after all 30 are uploaded to the database, it goes into this finished state, which blinks a white LED to the user, which tells the user they can turn it off. The Yun goes into a wait state, so it's not doing anything anymore. And then that's the end of the program. Then we have a schematic here of how everything's connected up. The only differences between the real pictures and this schematic are the indications of where the SPI communication to the ADS would be connected. The final picture is, on the left side we have a text file. That's an example of what would be stored on the external SD card and then uploaded to the database. And on the right here we have a couple examples of what's actually stored on Google. So at the top we have 2 files with date and time, each with a minute off, so those are the time files that are created, and that's their name, and that's how, and these are all updated at different times. That's why I did them in sets of 2 for testing. And that's my part.
Hello, my part is the Android application. The Android application serves as the output of the device. It's the only piece of the system that can interact with the doctor, so it has to meet with these criteria. It should be simple, fast, efficient, should be easy to use, and also has to be accurate. Here's an overview of the entire program. It has a login screen, a menu, and a graph. Okay. The login screen will be the first screen the doctor sees. It will prompt the doctor to enter his username and password, and the password will be hidden for security, and also will notify the user when wrong information is detected, and the user is allowed to re-enter information up to 3 times, and multiple users can be logged in at the same time as well. Okay. The main menu, this is the main part of the program. It downloads the information from the database. It would keep the useful information and ignore the rest, and then it would sort them by date and put them in a list form and display it. And the user can navigate through the list and select the file they want to see. Finally, the graph is when the user selects the file and it would download the information, graph the signal amplitude in millivolts, and plot them against time in milliseconds. And the user can zoom or scroll to get a better image. And the whole task could be done for less than 5 seconds for 10 seconds data, or less than 10 seconds for minute data.
We'd just like to conclude by thanking all the professors that helped us out. We'd like to shoot special thanks to Professor Curry and Dr. McBool for all their help. And we'd just like to say we had a lot of fun working together on this project, and thank you very much.
One quick word. Dr. McBool is our sponsor, and special thanks to Professor Kruger. He helped a lot in the power supply part.